This section will focus on the integrals that involve three of the inverse trigonometric functions: the integral of du over the square root of a squared minus u squared, which evaluates the arc sine of u over a, the integral which evaluates to 1 over a times the arc secant of the absolute value of u over a, and the integral which evaluates to 1 over a times the arc tangent of u over a. Now notice that we don't do the other three trig functions. That's because if you look back in section 5.6 at those rules for the derivatives, the only difference between sine and cosine, tan and cotangent, so on, etc., is a negative sign. So you can actually just choose to evaluate these as whichever the trig functions you want, give or take a negative. So we're only going to look at these three. So the first one is the integral of dx divided by the square root of 9 minus x squared. So we need to figure out which of our three forms this fits. And you can see that the u is going to have to contain an x. So the u contains an x. The a is going to be the constant. So since this one is written as 9 minus x squared, this means that we're going to be in the a squared minus u squared position. So this is an a squared is 9, so a is 3, and u squared is x squared, so that means that u is x. So since u is x, du is going to be u prime dx, which is just dx. So this is the integral of du divided by the square root of a squared minus u squared. And this evaluates to be arc sine of u over a plus c. You do need your plus c. So that's going to be the arc sine of u, which is x, divided by a, which is 3, all plus c. And that is my answer. With this one right here, we have something plus a 4x squared. So this means I'm going to be in the a squared plus u squared. So u squared is 4x squared, which means that u has to be the square root of that, or 2x. So du is going to be the derivative, which is 2 times dx. A squared is 3, so that means that a is the square root of 3. So this is the integral of, well, almost the integral of, we need a 2 and a 1/2. So this is 1/2 times the integral of du divided by a squared plus u squared. So this is going to be 1/2 times 1 over a arc tangent of u over a, all plus c. And then I just need to fill in my a and my u. So this is 1 over the square root of 3 times the arc tangent of 2x over the square root of 3 plus c. And from here I'm going to do a little bit of cleaning up. I'll multiply by root 3 over root 3 here and here. So that's going to give me root 3 over 2 times 3, which is 6, arc tangent of 2x square root of 3 over 3, all plus c. And that will be my answer. For the next one, notice I've got this x out here, which is a little bit extra, and I've also got the u squared in the first position. So here u is going to have to be 4x, a would have to be 5. So in order to make this work, I need to make it fit the form, the integral of du over u square root of u squared minus a squared, which means I need a 4x here, not just an x. So I'm going to multiply by 4 here, and I'm going to multiply by 4 here because it's like I multiplied by 1. They would just cancel. Now normally I put one of these on the outside, but in this case du has to be 4dx, so I actually need one on the top and on the bottom. So this is equal to that form without having to actually multiply by anything on the outside. So this evaluates to 1 over a times the arc secant of the absolute value of u over a plus c, which is going to be 1 over 5 times the arc secant of the absolute value of 4x divided by 5 plus c, and you can leave your answer there. This one is interesting, and it may not look like one of the forms to you at first. I've got the integral of dx over e to the x times the square root of e to the 2x minus 1. So we said that the u has to contain the x, so that means u squared is e to the 2x, and remember, you could write this as e to the x squared because if you raise a power to a power, you would multiply those powers. So that means u is e to the x, which means that du is the derivative of that, e to the x times dx. In this case, a squared is 1, so a is going to be 1. Now, I have u squared first here. So if u squared is first, this has to be eventually of the form du over u times the square root of u squared minus a squared, which we know is going to end up being 1 over a times the arcsecant of the absolute value of u over a plus c. But we don't quite have the form yet because we don't have u. Now, u is e to the x, so ideally I would be able to somehow get an e to the x here. We know that we cannot bring anything with an x to the outside of the integral, so I can't multiply by an e to the x on the outside. But if I can multiply by an e to the x on the numerator of the inside of this integral, then I will be in good shape. And it turns out that I can do that because I actually need, in order for to have du, I need an e to the x on the top. So this one does fit the form that I'm looking for. It's just someone went in and canceled out that e to the x from the top and the bottom. I'm just putting it back in so it fits. So this is going to be 1 over 1 times the arcsecant of the absolute value of e to the x over 1 plus c. And we don't need the absolute value because we know that e to the x is greater than 0, so we're in good shape here. This is my answer. Next, we're going to talk about some special techniques that you can use to evaluate. In this one, you've got the square root of x, you've got x plus 3 over the square root of 9 minus x squared. Now, a lot of people see this and they're tempted to write this as 3 plus x and then try and factor this and then cancel, and you kind of end up with this weird, like, the square root of x plus 3 divided by the square root of 3 minus x, but you don't want to do this because we don't know a form to evaluate that yet, so don't go down that route. The thing that you do want to do here is actually split up this numerator. So this would be x over the square root of 9 minus x squared plus 3 over the square root of 9 minus x squared. So I would have x, and I'm going to actually write this as, let's see, x, yeah, we'll do x over the square root of 9 minus x squared dx. And then I'm going to write this as 3 times 1 over the square root of 9 minus x squared, and let's go ahead and put the dx here. Now the reason why I'm doing it this way is because this allows me to fit two different forms for my integrals. So notice if I have an x here, I don't have an x here, so this is going to be the inverse trigonometric function. This one, though, I could write this as x times 9 minus x squared to the negative 1/2 power, and possibly do some kind of u substitution. So on the left-hand side over here, I've got 9 minus x squared, so if u is 9 minus x squared, then u prime would be negative 2x. So if I put a negative 2 here, I could divide by negative 2 on the outside. So this is going to give me negative 1/2 times the integral of u to the negative 1/2 du, which would be negative 1/2 times u to the positive 1/2 divided by 1/2, and the 1/2s would cancel. So from here, I would end up with a negative square root of 9 minus x squared. Now on this other side, if I let u be equal to x, du would be dx, and if I let a be equal to 3, this is going to be 3 times the integral of du over the square root of a squared minus u squared, which is going to be 3 times the arcsine of u over a. This is all plus c. So this is going to be 3 times the arc sine of x over 3, all plus c. And this would be my answer. I can't really simplify that at all. So sometimes you will end up just doing a straight up u substitution if you have the u prime in place, all the variables that you need for it. Without the x here, it turns into an arc sine. These are a little bit harder to recognize at first. They take some practice. You kind of want to think of yourself as a sculptor. You're trying to sculpt your integral into a form that you know and then apply that form. Another technique that can be a little surprising is when you have to complete the square in order to get a trigonometric integral. So in this case, if I tried to let u be x squared minus 4x plus 7, if I'm looking for a u prime over u or something like that, I would have u prime equals 2x minus 4. And I definitely don't have the x I need, so this is not what we want to do. We're going to have to look at this from a different perspective. So if I were to complete the square on the denominator, I have x squared minus 4x. I'm going to go ahead and kind of put the plus 7 out to the side. My b here is negative 4, so I'm going to add negative 4 over 2 squared, and then I'm also going to subtract that. This portion factors to be x minus 2 squared. This gives me plus 7 minus 4. So I get x minus 2 squared plus 3. So this is the integral of dx over x minus 2 squared plus 3. Now the reason why I did this is because if I let u be equal to x minus 2, then du would be 1 dx, a would be the square root of 3, and this becomes the integral of du over u squared plus a squared, or the integral of du over a squared plus u squared if you prefer, which is 1 over a times the arctangent of u over a plus c. So this is 1 over the square root of 3 times the arctangent of x minus 2, which is my u, over the square root of 3 plus c. And that would be my answer. And you can rationalize the denominator. At this point, I'm not really picky if you do or not, especially when you have more complicated answers like this. So this is one approach that you can take to integrate something like this. And that, to me, wouldn't look like an arctangent at first, but when you do some work on it, you can see that it actually does fit that form. Another one of these, this one is 1 over the square root of negative x squared minus 4x, and that negative inside the square root tends to trouble people, but if you complete the square, I'm going to factor out the negative, so I have negative x squared plus 4x, and then I'm going to add, the b here is 4, so b over 2 is 2, so I'm going to add 2 squared, and then I'm going to subtract negative 2 squared, the opposite of what I actually added. So this is negative x plus 2 squared plus 4, or you could write this as 4 minus x plus 2 squared. So this is the integral of 1 over the square root of 4 minus x plus 2 squared. And I'm going to go ahead and bump this dx up here. So my a squared would be 4, which means a is 2. My u squared would be x plus 2 squared, which means u is x plus 2. So du is 1 dx. So this actually does fit the form that we know, the integral of du divided by the square root of a squared minus u squared, which is the arc sine of u over a plus c, which is the arc sine of x plus 2 over 2 plus c, because that's my u and my a. So there can be some very surprising integrals that that end up being inverse trigonometric functions. Probably one of the hardest things that you'll have to do going forward, this test also, but when you go into Calculus 2, is being able to distinguish between integrals which evaluate to be inverse trigonometric functions, natural logarithms, and just a plain old like 1 over, or you know, u to the negative 1/2 like we saw earlier. It all basically turns out to be what form you can fit your function into. So if you don't have the x's that you need to do something like u to the n, then you're going to have to look at one of these other options. So that's probably one of the most challenging things going forward, and it just takes practice. The more you do at it, the more you practice it, the more you try it, the better you get at it, and the more intuitive it becomes. But you kind of want to think of yourself as an expression sculptor.